There's something very subtle about left and right-handedness in chemistry, and I want to give you just a little example. I'm going to use a carbon because this class is all about carbon, and I'm going to attach 3 hydrogens to that carbon. Now, of course, remember that's in tetrahedral style, so let's say that the hydrogens look like this. And on this carbon here, you can see that they're free to rotate around like a swivel, like a tripod on a swivel. So if I have something up here, like, I don't know, let's just make it another methyl group or something like that. That'll be fine. Because so long as you can swivel like this, then there's no odd configuration that you can make. There's no mirrored version of it. But I'm going to make some changes here, and we're going to see if that stays true. Don't want to blow the surprise for you, but things change. So let's take another carbon, and I'm going to put that same CH3 there. Just something different than the hydrogen. We'll have one hydrogen this way, and I'll have another hydrogen. We'll say it's coming out of the page towards us this way. And then what's leaving or going into the page away from us, we'll make it something else. Just some kind of O, maybe like an OH or something. I'm picking something random that's just not the same as the others. Still, this is free to swivel, and you would be fine if you drew something like HO, and then maybe like the H would be here, and an H here, and your CH3 up here. This could swivel around, and you would get this configuration here. And I'm going to keep changing these one by one, and we're going to see what happens here. So let's make a new carbon configuration. This time I'm going to make CH3. Then we'll have a hydrogen this way. This time we'll have, let's see, we already used O, so let's say like it's an NO, like some kind of nitrate on that end or something like that, and we'll have an alcohol this way. And I'm going to mirror it over here like this. OH this way, and we'll put an NO2 here, and we'll put the hydrogen over here, and we'll put the CH3 up here. And I got that carbon in the middle. So I'm going to put a mirror here because it's as if you're looking in the mirror, right? It's mirrored literally on the other side. But now if you notice with 4 different attachments to this carbon, if I was to swivel this around, this wouldn't be what it produces over here. Because if I swing this OH around, then what you're going to see is that the H should be here and the NO2 should be here. And in fact, if you look carefully, none of these can be rotated around or swiveled around in a way that this configuration comes out. And this is called chirality. This configuration is an enantiomer of this one here. And that is to say that they are opposite. That's what it means in Greek. But obviously they're not literally opposite. They're mirror images of each other, just like your left and right hand. They can hold up to each other, and you can match your thumbs and fingers, but you know full well that if you try to use left-handed scissors, well, it's not going to work out for you unless you're left-handed like me. So this is a really important concept in stereochemistry, and that's a subset here of organic chemistry. So this is something you need to know. And we can look at why that's different, why it matters, because that would be the first question I would ask is, why should I care? And the answer is, of course, that a molecule that is not identical to its mirror image, therefore is a stereoisomer, i.e. an enantiomer, behaves differently. Historically, this has been a real problem. Let me show you an example. And this is the most famous example. I'm going to show you 2 versions of the same molecule. Now this right here is called thalidomide. You probably haven't heard of it before because it's not a very famous thing to talk about. But one of these is different than the other in its chirality. Let's take black here, but you see here how this nitrogen is different than this nitrogen here. There's a flipped arrangement just in one spot. One is into the page and one is out of the page, but otherwise they seem identical. Well, one of these versions is a fantastic drug to deal with morning sickness. The other one causes horrible, horrible birth defects in children. It's a terrible, terrible thing. And I'm going to show you something here, just like a little bit of a graphic warning. But this is what one tiny difference in a drug does. I want you to see this here, because I want this to be in your mind. The deformation that this child experienced was due to the tiniest change in a molecule here. And that is so so impactful to me to pay attention to. So when I'm looking at this, it's very important to realize that when we're inventing drugs and we discover one that does a beautiful thing, that it helps women that are suffering, if we're not very careful with how it's made and how it's produced, the mirror image, this stereoisomer, which means it's made up of the same things and it's in the same molecular formula, but it's not configured the same, which makes it an enantiomer, can have drastically horrible consequences. We have to pay attention to how every single part of this molecule is arranged. So I wanted to bring that to your attention. So now we have to decide who's left-handed and who's the right-handed version. And there's rules for this. Big surprise, I know. But let's take this bonded up carbon here as our example since it's already out. And the way we're going to label this is for each of these substituents attached to the carbon here, we're going to look at the highest atomic number and make that number 1. And we're going to go around and do that. So this would be number 2, and then this would be number 3, and this would be number 4. And then we're going to draw an arrow so it would look like this. And then that'll be like the top of the tetrahedron. So what I could do is I could draw the tetrahedron like that, and then I would have these down here like this. So that's what that looks like. And because this is clockwise, then this is going to be R, or right-handed or clockwise version of it. And when I look at the other version, well, here's going to be rank 1 here because oxygen is the highest atomic number. And then we're going to have this guy, and then this guy, and then this guy. So we would have counterclockwise here. That's the L enantiomer. And this works throughout. It's really as simple as that. So if you can learn this rule, you can learn how to count this up, then you're going to be fine. This is all it takes. I think we'll just move on from chirality and start working on some fun stuff, and this will mix in as we go forward. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.